Okay. Let's see. All right, so let's finish up our last three examples over the chain rule, and then we'll move into next section of material. All right, so the last set of examples that we're going to deal with is doing implicit differentiation. So the first example we have is this. We have that xy plus y squared minus 3x minus 3 is equal to 0. And we're given the point of negative 1, 1. Okay, so what we're going to do is to find dy dx. All right, so if we find dy dx, all right, and we're going to use partial derivatives to help us with this. So this is going to be equal to the negative of partial in respect to x over the partial in respect to y. Okay, so if we take a look at the problem that we have, all right, so starting on in the numerator, if we do the partial in respect to x, we're going to have y minus 3. And then in the denominator, if we do the partial in respect to y, we're going to end up with x plus 2y. So now, basically, we're saying that dy dx is equal to the negative of y minus 3 over x plus 2y. Okay. So if we want to evaluate this at the point negative 1, 1, so we're going to have negative of, if I put negative 1, I'm going to put 1 in place of y. So I have 1 minus 3 over negative 1 plus 2 times 1. So I have negative 2 over 1. So I get a value of 2 for the dy dx. Any questions? All right, so for the second one, okay, we are given that b, this is for the second one, we're given that 1 over x plus 1 over y plus 1 over z is equal to 0. And we're given the values of 2, 3, and 6. Okay, so this time I'm going to switch it up a little bit. I want to find the partial of z in respect to x. I'm going to find the partial of z in respect to x. All right, so if I do this, all right, again, it's going to be the negative of, we're going to do the partial in respect to x over the partial in respect to z. Okay. All right, so if I do the partial in respect to x, what will I get? If I do the partial in respect to x, what will I get?
Negative 1 over square, a square.
Okay, 1 over x squared. All right, so next, if I do the partial in respect to z, what will I get? Okay, negative 1 over z squared. All right, so we can clean this up, and it's going to end up being negative z squared over x squared. Okay? So this is what the partial of z in respect to x will be equal to. All right, so if I evaluate it at the point 2, 3, 6, okay, so if I evaluate at the point 2, 3, 6, I'm going to have negative of 6 squared over 2 squared. So this is going to give me a value of what?
Nine.
Yeah, negative 9. Okay, it's going to give me a value of negative 9. Any questions? Now, one of the things I do want you to keep in mind that when we have three variables, like I can do the partial of z in respect to x, I could do the partial of z in respect to y. Okay. Any questions? Okay. All right, so now let's look at the last one. So the last example, I have that x e to the y plus y e to the z plus 2 natural log of x minus 2 minus 3 natural log of 2 is equal to 0. And we are given the point 1 comma natural log of 2 comma natural log of 3. Okay, so in this one, I want to do the partial of z in respect to y. Okay, partial of z in respect to y. So if we do this, it's going to be the negative of the partial in respect to not x, but y divided by the partial in respect to z. Okay. So if I do the partial in respect to y, what would I end up with?
X is e to the power y, and plus e to the power z.
Okay. And then next, if I do the partial with respect to z, what will I get?
Y e to the power z.
Y times e to the z. Okay. All right, so we're going to have this. All right. So this is what the partial of z in respect to y is going to be equal to. So now what I want to do is do the partial of z in respect to y and evaluate it at the point. Okay. So if I do that, I'm going to have negative of, all right, so in place of x, I'm going to put in 1. In place of y, I'm going to put in the natural log of 2. In place of z, I'm going to put in the natural log of 3 over the natural log of 2 times e, forget, e to the natural log of 3. Okay? So the numerator, when that simplifies, what does it simplify down to? Yes, it simplifies down to just 5. And the denominator is going to simplify down to just what? Yes, 3 natural log of 2. And don't forget the negative. So this will be our value.
30 seconds until minions spawn.
Any questions?
Are restless.
I have a question. So you
Mhm.
know what is to use to find DYD the derivative DYDX? Like, would it be like is it fine? Like if it's a partial derivative? Like I'm confused.
Minions have
What?
spawned.
Because the question, like the example says, use implicit differentiation to find DYDX. So
Right. So what we're doing is that
mhm.
we are using partials in order to find that. So if I do actually work this out to do it in terms of implicit, okay, I'm going to get this answer right here.
Oh, okay.
Okay.
Yeah.
So
Confused.
what it's doing is that it's saving you all that trouble. I got to use the product rule here to take the derivative of this. Chain rule here, and then this is just a regular rule. This is going to be 0. So I don't have to do all that and then solve for dyd and then solve for y prime or dydx.
Oh, okay. Now I understand.
Yeah. So basically, what this is doing is we are. It's basically a shortcut for us for doing implicit differentiation, so that we don't have to go through that long route we learned in Calc 1.
Mm-hmm.
Okay.
Okay.
Any other questions?
From above.
To the last one, or is this one? Okay. You're welcome.
I think I'm confused in this part. Like whether to use like partial z over partial x or partial z over partial y. Like how do you determine that?
Well, the problem will tell you which one to do. Okay. So keep in mind that when you are dealing with 3 variables, becomes that you got to deal with partials. Okay. If it's just 2 variables, then it becomes just dy dx.
Oh, I see.
Okay.
Mm-hmm.
Any other questions? Okay. So this concludes everything for the midterm. Okay. So the midterm, you have to have it completed by March. I think I've got it set for March 18th. Okay. It's going to be open starting on the 17th of March and close on the 18th of March. And the 18th of March is a Thursday, so since that's the end day of your test, it will not be any. There will be no live class time that day. Okay, so you'll have basically over 2 days to do it, but there's a catch. Okay, so unlike the quizzes are on time. This test is timed. You have 3.5 hours to complete. Okay, so you have 3.5 hours to complete. Now, as far as the test is concerned, it's open notes. Okay, so you're not restricted to try to do this without any having your notes open or anything like that. And so it is open notes. All right, so just keep in mind that you do have to make sure you show all your work and everything. If I remember correctly, there's a total of 15 questions. Okay, now as long as you've got your notes in order and kind of have an idea of where things are at and everything in your notes, then it shouldn't be any problem with the as far as the test is concerned. Just keep in mind that as far as materials concerned that we've covered so far, the big things that we've been dealing with is dealing with vectors. Okay, so that's going to be the majority of the material that will be as far as the test questions are concerned. Okay. Questions? No. So once the test is open, you've got 3.5 hours to complete it, upload it, get it done, and upload it. So there's no opening and closing. All right. So once you start, you're in. Now, it may not take you 3.5 hours to complete the test, and that's perfectly fine. It's not designed to take you that long, but just keep in mind that I'm just giving you the time so you don't feel like you are that you feel like you're being rushed in order to do it. Okay. It opens at midnight on the 17th and closes at 11:59 on the 18th. Okay. Any other questions? Okay, so typically in this class, I never stop teaching. So pretty much I'm going to follow that rule. The only day that you basically get off is that test day. There will be no class that day. But typically I just move on into the next material. So the next set of material is all the material that is going to be focused on the final. Okay, so basically what we'll do is we'll finish up the material for dealing with differentiation, and then we'll move into integration. So that means that the final will be heavy, very, very heavy on integration. No, the final's not cumulative. They're two separate tests. Any other questions? Okay, so let's go ahead and get started. All right, so this is now we're moving into material for the final. All right, so we're going to move into the section dealing with directional derivative. And gradients, gradient vectors. Okay. So we're going to move into stuff dealing with directional derivative and gradient vectors, right? So basically what we are looking at as far as a gradient vector is concerned. So this is going to basically, we're going to be creating a vector, but we are going to be using derivatives to help us with this. Okay, so what we say, if we say we want the gradient of f, all right, so the gradient is this upside down triangle basically, of f, and what this is going to be equal to, we're going to have the partial of f in respect to x in the I direction, plus the partial of f in respect to y in the j direction. Okay. Now, if it's a three-dimensional vector, so say we want to find gradient of g, so it would be the partial of f in respect to x in the I, plus partial of f in respect to y in the j, plus the partial of f in respect to z in the k. Okay. All right. Any questions? Okay, so basically when we are, and this is dealing with, again, the gradient vector. Okay, so if we are taking a look at what we refer to as a directional derivative. Okay, so for a directional derivative, the kind of the notation we use, we say d sub u of f. Okay, so the notation we use is d sub u of f. Right? So the directional derivative is going to be equal to the gradient vector dotted with some vector u. Okay, so it's going to be the gradient vector dotted with some vector u. And normally the gradient vector is going to be evaluated at some point. Okay, so that way when we do the dot product, we actually get a numerical value instead of a new vector. I mean, yeah, when we do the dot product, we get a numerical value and not some expression in terms of variables. Okay. All right, so what we're going to do is to take a look at some examples, show you how this is going to work. Okay. So first example we're going to take a look at is this. So we are given a function g of xy, which is defined as x squared over 2 minus y squared over 2, and we're given a point of square root of 2, 1. So for part A of this, we are asked to find the gradient of g. So part A of this, we're asked to find the gradient of g. So what we're going to do is, the way we're going to do this, it's going to be the partial of g in respect to x in the I direction plus the partial of g in respect to y in the j direction. Okay, so if we do the partial of g in respect to x, we're going to end up with x in the I direction. If we do the partial of g in respect to y, we're going to end up with negative y, and it's going to be in the j direction. So our gradient of g is defined as x in the I direction minus y in the j direction. Any questions? Okay, so now part B of this question is saying, okay, you found the gradient, now evaluate it at the point. Okay, so we said that the gradient was defined as x in the I direction minus y in the j direction. So in place of x, we're going to put in square root of 2. In case of y, we're going to put in 1. And this would be our gradient evaluated at the point. Any questions? Okay. All right, and then C, it wants us to graph the level curve for G at the square root of 2 comma 1. Okay, so it wants us to graph the level curve for G at the square root of 2 square root of 2 comma 1. Okay, so if we take a look at that, okay. All right, so if we take a look at that, all right, so our, oops, sorry, too far. Original function was this, okay? Well, if we look at this, this is basically the standard form for what? It's not going to be a circle because you got subtraction. Okay, yes, it's going to be a hyperbola. Okay, yes, it's going to be a hyperbola. So if we take a look at this, all right, so what we're going to end up having is we're going to have this. Okay. So if we were to plug this point in, so if we do g of square root of 2 comma 1, so we're going to have the square root of 2 squared over 2 minus basically 1/2. So we're going to get 1/2. So this is what the function will equal to. So what we're going to do is say that this is going to be x squared over 2 minus y squared over 2 is equal to 1/2. Essentially what we can do is multiply everything by 2. So we get x squared minus y squared equals 1. So this would be the standard form. So we know it's at, we're starting at 0, 0 for the center of this hyperbola. And then basically we're going to go 1 unit in all 4 directions. Okay. We can create a box. And then we can put the asymptotes in there, which are the diagonal of the square. Okay. And since x is first, we know what opens left and right. Starting in this point, curving over, and this point, curving over. So it looks like this. Okay. Now, the other thing we're going to do is we're going to put on, we can put the gradient on here, okay, which we said the gradient was, oops, sorry, wrong page. The gradient was this at that point, okay? So what that tells us is that we're going to be on the curve. Let me switch colors. We're going to be on the curve, which is, we're going to go square root of 2 over, so 1 a little bit more, a little bit past 1, and then we're going to go down 1 on y, so down 1 here, So this would be the vector. The gradient G, okay, based on this. Okay. Any questions? Okay, so let's look at another example. All right, so for our next example, all right, this time we're told that f of xy is equal to the natural log of x squared plus y squared, and we're given the 0.11. Okay, so to start off, part A, we're going to find the gradient of f. Okay, so if we find the gradient of f, what's going to be the first term?
Partial f over partial x.
Okay, so we're going to do the partial of f in respect to x. So what would that be? So what would the partial of f in respect to x be?
Two x over x squared plus y squared.
Correct. Okay, so 2x over x squared plus y squared in the I direction plus, and then for the second one, it's going to be the partial of f in respect to y, and what would that be? Yes, that's going to be 2y over x squared plus y squared, and that's going to be in the j direction. Any questions there? All right, so part B, we want to evaluate the gradient of f at 1, 1. Okay, so if we evaluate the gradient of f at 1, 1, what's this going to be equal to?
Two in the I direction and two in the j direction.
Be careful. Yeah, it should be just 1 in the I
Oh,
direction
cancel out.
plus, and when we evaluate this at 1, 1, it's going to be 1 in the j direction. Any questions there? Okay, so part C is asking us to do the graph of the level curve at 1, 1. So graph level curve at 1, 1. Okay, so if we do that, we basically are looking at this. So we have, if we look at f of 1, 1, we're going to basically end up with the natural log of 2. So our equation for the level curve is going to be the natural log of x squared plus y squared is equal to the natural log of 2. But really, this is going to be equal to what? So what does this simplify down to? It's going to be a circle, so but what's our equation?
A squared plus y squared equal to 2.
Okay, so x squared plus y squared equals 2. Okay, so this is what we're going to end up with as far as the equation for the level curve to be. So if we graph this, we know it's going to be 0, 0. It's going to have a radius of a little bit bigger than 1, but not quite 1.5. And this will be our graph of our level curve. Okay. All right. And if we put the gradient on here, so the gradient is 1, 1. So 1 over, starting here. In the case of this, we can get away with looking at it starting from here and going over, okay, this way. And this will represent the gradient of f, because actually the gradient's not going to be on the circle because of how it's defined. Any questions? Okay. All right, so now let's look at our next example. Okay. So our next example, we are given that f of x, y, z is equal to 2z cubed minus 3 times x squared plus y squared times z plus the tangent inverse of xz. And we're given the 0.111. Okay, so part A, we're asked to find the gradient of f. Okay, now since it's 3 variables, that means we're going to end up doing 3 partials. So that means that it's going to be a vector in I, J, and K direction. Okay, so our first piece is going to be the partial of f in respect to x. So what would our partial be in respect to x?
Negative 6x
Okay, so we're going to have negative 6x.
plus.
Let's be careful. So it's going to be negative 6xz. Okay.
Oh,
Plus, and then we're going to have z over 1 plus xz squared. And this is in the I direction. Okay. Plus, all right, so what would be our partial in respect to of f in respect to y? Yes, it will be negative 6yz, and that's going to be in respect to in the j direction. Okay, plus, now we need our partial in respect to z. And unfortunately, I'm going to run out of room, so I'll write it up here, but then I'll transfer it to the next page. So what will be our partial in respect to z?
Six z squared
Okay,
negative 3a squared plus, I mean, like the negative 3a squared, negative 3y squared. Yeah, like
okay,
3 squared. And plus x over 1 plus xz squared.
so that would be, and this would be in the k direction. Okay, all right, so let me rewrite this on a new page. Okay, so the gradient of f is going to be equal to, again, negative 6xz plus z over 1 plus xz squared. This is in the I direction, plus negative 6yz in the j direction, plus, then we're going to have 6z squared minus 3x squared plus y squared plus x over 1 plus xz squared, and this is in the k direction. Any questions there? Okay, so the next part is that we want to, part B, take the gradient and evaluate it at the point 111. Okay, so if we evaluate the gradient at 111, so for the first term, we're going to have negative 6 plus 1 over 2 in the I direction, plus, then we're going to have negative 6 in the j direction, plus, and then the final one, we're going to have 6 minus 3 times 2 plus 1 over 2 in the k direction. So this should clean up to give us, look at this, let's see, negative 11 halves in the I direction, minus 6 in the j direction, plus 1 half in the k direction. Any questions? All right, so let's go through one more example and then we will take a break. Okay. All right, so the next example is going to be focused on us dealing with the uh, basically a directional derivative. Okay, so we are asked to find the derivative of a function at p sub 0 in the direction of a. Okay, so if we do that, in this example, we are told that f is defined in terms of xy is equal to 2x squared plus y squared. We're told that the point p sub 0 is defined as negative 1, 1. And we're told that the vector a is defined in 3 in the I direction minus 4 in the j direction. Okay. So the first part of this, they want us to find the unit vector for a. So the unit vector for a is going to be 1 over the magnitude of vector a. Well, that's going to be the square root of 9, not 9 squared, but just 9 plus 16. Then we're going to multiply by that vector, so 3 in the I direction minus 4 in the j direction. So our unit vector should be 3/5 in the I direction minus 4/5 in the j. Any questions there? Okay. Part B, we want to find the gradient of f at p sub 0. So what we're going to do first is to find the gradient of f. So if I do the gradient of f, I'm going to do the partial of f in respect to x, and we should get 4x in the I direction, plus, then we're going to do the partial of f in respect to y, which is going to be 2y in the j direction. So now, what we want to do is evaluate at the point negative 1, 1. So if I do that, I get negative 4 in the I direction plus 2 in the j direction. All right, and then part C, we want to find the direction, basically the directional derivative of this. So we want to do du of f at p sub 0. So that means what we're going to do first, we're going to do the gradient of f evaluated at p sub 0, and we're going to dot it with the unit vector. Okay, so the gradient of f evaluated at p sub 0, we found to be negative 4, 2. And then the unit vector we found to be 3/5, negative 4/5. So if we do the dot product here, we're going to end up with negative 12/5 minus 8/5, which is going to give us negative 25/5, not fourths, which is going to equal negative 4 over in the quarter. Any questions? Okay. All right. So at this time, let's take a 10-minute break and then we'll start back up. So we'll start up about 12:12. I mean 12:12. 12:02. Okay. Any questions? Okay, so let's look at our next example here. All right, so for our next example, so it's basically going to be the same thing, but this time we are going to create, we're going to create a three-dimensional vector and do the dot product for it. Okay, so in this example, we're told that f of x, y, z is equal to x squared plus 2y squared minus 3z squared. We are told that the point is defined as 1, 1, 1, and the given vector A is defined as 1 in the I direction plus 1 in the j direction plus 1 in the k direction. Okay. So again, the same thing, we're going to do what we did last time. So the first part, we're going to find a unit vector for A. So our unit vector is going to be 1 over, all right? So what would be the magnitude of vector A? Yes, square root of 3. And then we're going to multiply it by I plus j plus k, all right? Or we're going to get 1 over the square root of 3i plus 1 over the square root of 3j plus 1 over the square root of 3k. Okay? Any questions there? All right, so B, we're going to find the gradient of f at f of p sub 0. So the gradient of f, all right, so we're going to do the partial of f in respect to x, and what will we get for that? Okay, so we're going to have 2x in the I direction, plus, then we're going to do the partial of f in respect to y. We're going to get what? We're going to get 4y in the j direction. Then we're going to have minus, and then what is going to be the partial of f in respect to z? Yes, it's going to be 6z in the k direction. So if we evaluate the gradient at p sub 0, considering that all the values are 1, so this makes it pretty nice. So it's going to be 2 in the I direction plus 4 in the j direction minus 6 in the k direction. Any questions there? All right, and then part C, we're going to do the directional derivative at the value 1, 1, 1. So that means we're going to do the gradient at that point dotted with the unit vector. So we're going to have 2, 4, negative 6 dotted with 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. Oops. So if we do this, we're going to have 2 over the square root of 3 plus 4 over square root of 3 minus 6 over the square root of 3. And that's going to give us a value of what? This is the value of 0. And there's our answer. Any questions? All right, so we've got two more examples that we are going to deal with. So the first example, okay, we're going to find the directions in which the functions increase or decrease the most rapid at p sub 0, then find the derivative of the function in these directions. Okay, so first of all, so in this next example, we are told that f of xy is defined as x squared y plus e to the y, e to the xy. All right, and times the sine of y. And the point we are given is 1, 0. All right, so in order for us to do this, all right, so the first thing we're going to do is we're going to find the gradient of f. All right, so if we do the gradient of f, so what would be the partial in respect to x? So what would the partial be in respect to x? Partial of f in respect to x.
To xy
Okay.
plus y e to the power xy.
Okay. Anything else?
And sine y.
Yes. You can't throw that away. Okay. And this is going to be in the I direction. Plus. All right, so now we need the partial in respect to y. And what would that be?
One plus.
Let's see. So we should have x squared plus.
Oh yeah, x squared, my bad. X squared plus x e to the power xy and cos y.
So
Oh, sorry.
x,
Yeah, I think
y,
it has to
so
be
times the sine of y.
Yeah, product rule.
Then plus, then it's going to be e to the xy times the cosine of y. And this is going to be in the j direction. Okay, so next, we've got these, so we're going to find the value of the gradient at p sub 0. Okay, so if I put in the point 1, 0 into this, what will I get? If I put in a value of 1, 0 into
Zero.
this, I get 0. So I get 0 in the I direction plus if I put in the values 1, 0 into this, what will I get?
It's gonna be 2.
Yeah, I get 2 in the J direction. Okay, or I would just simply say it's 2 in the J direction. All right. Any questions there? All right, so part B, we're going to do a unit vector for the gradient of f. Okay, so the unit vector is going to be the gradient of f over the magnitude of the gradient of f. Well, the gradient of f is equal to 2 in the I direction. What's the magnitude of the gradient of f?
2.
It's 2. So we're going to end up with just I. I mean, excuse me, with just J. Okay, so we can say this. Okay, so now we've done all the preliminary work. So now we're ready to answer the question that this problem is asking. Okay, so we can say that F increases most rapidly when U is equal to J and decreases most rapidly when negative U is equal to negative J. Okay, so it's going to increase the most rapidly in the positive aspect. It's going to decrease the most rapidly in the negative aspect. Okay, so the last thing that we are asked to do for this is to just find uh, the derivative of the function, the direction. So we're looking for the directional derivative. So if we do the directional derivative of u of f evaluated at p sub 0, that's going to be the gradient evaluated at p sub 0 time dotted with the unit vector. Okay, so essentially this is so if we look at this, the gradient evaluated at this is going to be 2, well, it's actually the vector is 0, 2, dotted with 0, 1. So we're going to get an answer of 2. And then if we look at it in the negative sense, where it's growing, when it's decreasing most rapidly. So again, it will be evaluated a piece of 0 dotted with the negative of this. So to be 0, 2 dotted with 0, negative 1. So we get negative 2. Any questions? Okay. All right, so the last thing we're going to take a look at is writing an equation for of a line tangent to the curve given. We're given what the function is defined as. We're going to find the gradient, and then we're going to write an equation of the. We're given the equation formula for the tangent line. Okay, so let's take a look at this particular problem. So in this example, we're given the equation x squared minus y equals 1, and we're given the point square root of 2 comma 1. Okay, so the first thing we're going to do in order to do this, all right, so the first thing we're asked to do is to find the gradient of f at the point. Well, first we need to put this into a function notation. So if we put it in a function notation, we're going to say this f of xy, and that's going to be equal to x squared minus y minus 1. Okay, and simply all I did was to say, okay, I need this equal to 0. So I have x squared minus y minus 1 is equal to 0. Replace 0 with f of xy. Okay, to put it in function notation. Any questions there? So for part A, if I do the gradient of f, so I'm going to find the partial in respect to x. So I'm going to get 2x in the I direction. Okay, plus then the partial in respect to y is going to be -1 in the j direction. All right, so, or I can write this as 2x in the I direction minus 1 in the j direction. So now I'm going to evaluate the gradient at the point square root of 2 comma 1. So if I evaluate it at the point, that means I'm going to have 2 times the square root of 2 in the I direction minus 1 in the j direction. Any questions? All right, so part B, we are going to write an equation of a line tangent to the curve. Well, the formula that we're going to use is a times x minus x of 1 plus b times y minus y sub 1 is equal to 0. Okay. Now, you have to remember that for the tangent line, basically what we need is the slope, okay, in order to write the equation. Now, in order to find the slope for a tangent line, we need the first derivative. Well, considering that we are working with a gradient, we have the derivative, okay? So a is going to be associated with the I component. So in place of a, I'm going to put in 2 times the square root of 2. Then we're going to have x minus x of 1 is the x coordinate of the point, which is the square root of 2. Plus b is going to be associated with the j component, which in that case, the coefficient is -1. So we're going to have y minus y sub 1, which is 1, and is equal to 0. So essentially, what we can do is put this in slope-intercept form. Okay, so we're going to multiply this out. And if we do that, we're going to end up with 2 times the square root of 2, 2 times the square root of 2 times x minus 4. Okay, and then minus y plus 1 is equal to 0. So basically, I want to get y by itself. So what I'm going to do is add y to both sides and then combine like terms of what's left. So I'm going to end up with 2 square root of 2 times x minus 3. And this will be my equation. Any questions? Okay, so this is where we're going to stop at today. Okay, so you need to make sure to complete the homework over chain rule. Okay, I think quiz 9 is okay. Quiz 9 is not due until it's not due for a little while, so you're still good. So quiz 9, and it's not open yet, so ignore that. Okay, so you need to work on the homework over the chain rule. I would suggest to start on the directional derivative. Okay, I do have that available. I don't think I have the solutions to it, but I will get those up here. I'll get those up over the weekend. Okay, but your main homework is to complete chain rule, right? And have questions ready to go for that on Tuesday. I've got the answers posted for that. There's a couple of them that we'll do in class, and it's just because they're drawings, and it's easier for me to draw them in class than it is to try to put that in the consistency of the answers. Okay? Any questions? All right. So you guys have a great rest of the day. You have a great weekend, and I will see you on Tuesday.